And I'm pretty much going to have you do, you know, full-blown reduction of order. So I'm going to have to hand pick some problems. It's not going to go too insane. Yeah.
Is that the section where you said there's like a shortcut?
Yeah, there's a shortcut to it. Yeah. But, you know.
I tried finding it in the book. I couldn't see like.
Very end, right before the homework section. It's in blue right up there. A little integral with e to the integral p. It should look very familiar. But I want you to know the steps to doing it, right? Yes?
Do we have to know the shortcut?
Are you able to know it? Sure. Can you check your answer with it? Sure. Is it going to be good enough for me to show that? No. So, again, I'm going to kind of hand pick a problem. It's not going to get too insane.
So we don't have to know it.
Say again?
We don't have to know it.
You don't have to know it. No. Hell no. Shit, you don't have to know any freaking shortcuts ever. Do you understand? In fact, to me, I think we teach, or some teachers teach way too many shortcuts. And then you lose touch with why they work. And then you lose touch with stuff that you could make connection. I know. Okay. So let's see. 4.2 is all about, and so what do I have to give you to get 4.2 rolling in a problem? What do I have to give you? Yeah, I've got to give you an answer already. And now, one quick little place where it actually makes a ton of sense is with that repeated real roots case. Without the reduction of order, we would have no real way to find that second answer. And we do have one answer. We just don't have the second answer. So reduction of order, if it didn't exist, we'd be screwed. So when you first do it, you're like, well, this sucks. I have to know the answer before I can find the other one. But that's an immediate place where without it, we couldn't do anything. So I think on the practice test, they give you, well, you know, like number 2, that's what number 2 is all about. Repeated roots, actually. Where's the other answer come from? Reduction of order. What's the answer to number 1 on the practice test? You got to be like, why didn't you give that to us on the actual test? You're telling us what to do. Damn you, Jim. Well, that's why, pretty much. But why does it make sense that y2 equals u?
To be linear and that has to be y2 over y1.
Yeah, y2. If y2 over y1 was a constant, that would mean that those two functions are linearly. If y2 over y1 was a constant, they would be dependent. One would be a constant times the other one. That's totally dependent. One depends on the other one. So if y2 divided by y1 is some function, then they're independent. So that's our first step into the idea. And again, a really good reason. So that's the most direct reason why it makes sense to that this would work, that this actually leads somewhere. But to be honest, you can make y2 equal u times whatever you want it to be. But why does it make sense to build it off of y1? Because what does y1 do to the thing? Makes it 0. So in that derivation for the variation of parameters, which is another place that we do something sort of like this, we saw that the y1 and y2 pieces made whole chunks of the thing go to 0, which makes sense. That's what they do. That's where they come from. This makes sense so far. I mean, what's really kind of hilarious here is I could say y2 equals a of x times b of x divided by y1 if I wanted to, and just work with that shit. And it would work. Oh my God, it would work, but it would be disgusting as all shit, right? But because there is a y2. There's that uniqueness in the second order is what we're working with here, right? So I know there's going to be 2 answers to this. And for some a and some b, and when I divide by y1, it will be the function it's supposed to be. So there's even greater flexibility than I sort of showed you, because this just doesn't make any damn sense, really. I want to build it off of that directly. Yes?
How do we know that there's not some y3 function that is also a solution? How do we know when we've gotten all the solutions?
So it's sort of related to the fundamental theorem of algebra. The number of answers to a polynomial equal to 0 is going to be equal to the degree of the polynomial. So in this case we have, I can't remember exactly where they said that. It was buried in one of the sections where they talked about if you have a third order homogeneous equation, you're going to get 3 answers, right? What's beautiful about this is if we get 3 repeated roots, they actually relate to 3 distinct functions. They have to because of the linear independence requirement. If I have a polynomial, it's got 3 answers, they all happen to be the same answer. It always felt a little bit, it's got one answer too, but it shows up 3 times. It's like, all right, whatever. It always felt a little, to me anyway, it felt a little bit like, there's really 3 answers. Here, they have to be linearly independent. It's kind of more fulfilling. There are 3 distinct answers for a third order DE homogeneous, right? Now for YP stuff, it could be any number of parts it needs, to be honest. There's no guarantee as to how many little pieces, how many terms are going to be there, because it's one function. But for a homogeneous, C1 times something, C2, those are each functions have got to be as many as the order of the homogeneous DE was. I like it. I like it. I can't remember, if somebody can remember where they discussed that little piece, but it's very much related to
134 or 135. Page 135.
135? Oh, so close. It's right next to it. Blah, blah, blah. Blah. Blah, blah, blah. Blah, blah, blah. Blah, blah, blah. Oh, yeah, this is sort of waving the hands a little bit. It's too specific. I thought somewhere there was something a little more. This is almost too specific to that case of that kind of DE, but there's a more general rule about the order of something and homogeneous DE and how many answers you can have. Okay. So at this point, if you've done the homework and you tried to use the full-blown and not just the shortcut, I was letting a few people do a few shortcuts, but if you did the shortcut in every problem, no. Do at least the first 3 problems with the full-blown, because they're not that bad. Some of the later problems get a little more disgusting, and some of you guys that tried to do it without the shortcut, I applaud the hell out of you. They get really kind of bogged down, but it'll still work. So as long as I don't let it get too disgusting in the middle, this method is not that difficult. I feel very comfortable saying that. Okay, I'm going to have to supply you with the Y1. I like it. Okay, so is there an example of this? Did I actually put an example of this? No. It's sort of buried in there a little bit, I think. Was there one of these you needed to use that? Not really.
You can use 4-3.
Yeah. Yeah, except for like 4, what about 4D, I think was possibly one. Maybe not. I'm not thinking about that right. Variation parameters is what I'm thinking about. I could still give you, because the first 2 basically are talking about reduction of order, so I could still give you a reduction of order problem, so just be ready for that. Any questions on 4.2 by itself, reduction of order? You guys want to do an example problem? Yes, okay. Let's take one right out of here. Let's do one that's a little bit different here. Blah, blah, blah. Yeah, let's look at this one. So I get, they give me that y1 is x squared. So then,
Y equals Y1 times U.
yeah, y equals u, y1, which y equals u, x squared.
And then Y.
And then you just, so it feels a little bit like what you do with undetermined coefficients. But what you're doing now is not based on the answer, obviously, because the answer is 0 here. It's based on the other answer. So y equals, y prime will be, yeah, just go to 10. Yeah. Not u, Jeff. And y double prime, u double prime x squared plus 2u prime x plus 2u prime x plus 2u. All right, let me stop there for a second. So pretty much, I give you an answer that immediately tells you what to replace y with. U times that answer. U is a function of x, so when you take derivatives, you got to be careful it's a product rule. A lot of us are being very careless with product rules and stuff like that. Makes things go really fast, but you get to the wrong answer without wasting a lot of time, which is nice and bad. So then you get, let's see, you get u double prime x to the fourth plus 4u prime x cubed plus 2ux squared plus 2x cubed u prime. Is this cool? You guys see it? 2x times that. 2xy prime. And I like what some of you guys are doing, actually. It's kind of neat. You're putting next to this like negative 6y equals negative 6u x squared. And you put here 2xy prime equals, and then you're writing what it is. You're building the parts you need, and then you can just put them together. Beautiful. I love it. Construction approach. Where am I at? 2u prime, let's see, 2x times this stuff, so that'll be plus 4ux squared. And then minus 6y, so minus 6ux squared. Remember, what is it about this that tells me I'm on the right track?
When the u cancels out.
Yeah, when everything that has the non-derived u piece, that just the u by itself, when all those cancel, at least those have to cancel. Maybe more will cancel. In this case, they don't. Plop. If the u stuff doesn't cancel, something's gone wrong. You didn't do the derivatives right, something went wrong. Now what do I do here?
Plug in your w equals.
And what else can I do? Yeah, so you can say w prime x to the fourth plus 6wx cubed.
Subtract the side.
Sure. And now, what approach could you take to this?
Oh, is it stuff we learned?
Separable or linear, right? So separable, so you get, subtract that, you get dw over w equals negative 6. Now it'll be x cubed, but then you can divide by x to the fourth, so negative 6 over x dx. Right, because what's w prime? dw dx. So you can have dw that side, multiply dx up that side.
You can just score if you're doing linear. Your p of x is 6 divided by x.
Yeah, and once you divide by x to the fourth, you can see what your p of x is going to be. It'll be 6 over x. You can integrate e to the interval of that. So you can do linear.
Will it always be one of those? Like with,
Always. Yeah, that's the beautiful thing about reduction of order. It's always one of those two.
is it always both? Or,
Oh, man. Off the top of my head, I'd say maybe.
okay.
I think it is, but I can't remember.
What was that last part you said? Either separable or you can use an integrating factor?
Yeah, this one you could use, when you divide by x to the fourth, it's linear in w. So you could use integrating factor, it's linear, or you can separate it, which is the most direct route. Separable is the one that feels most like 180. Which now, you might have hated the first time around, but now you're missing 180. All right, is this cool? So you get natural log w equals negative 6 natural log of x. So you get natural log of 1 over x to the 6th. Is that cool? I don't need that anymore. Plus c, but we're not really there yet. We have to get what w is. And then w is u prime. So we get w equals 1 over x to the 6th. Does everybody see that? Is that cool? This is a negative 6 constant. I get natural log of x. Negative 6 in front goes up as a power. So it's 1 over x to the 6th. I like it. Sometimes you guys get the new stuff and then the old stuff is what kills you. Change sometimes to most of the time. And then, what's W?
U, and then that's.
U prime? So then U is going to be the integral of that. And what's the integral of x to the negative 6?
Negative 1 over 5, that's negative
Yeah, so the power goes up, so it would be negative 1/5 x to the negative 5th plus c. And then you go back to what got things started off. Now, I think the book sometimes leaves out that plus c because it's only getting the second, but what I love is to see that it picks up both answers. So now y equals u times x squared. So I get negative 1/5 x to the negative 3 plus c x squared. So what's the new function? What's y2? Let me ask you a few questions. What's y2? Here's y1. What's y2?
Negative 1/5 x to the negative 3.
Sort of. Just x to the negative 3, right? So what's yc?
X squared. C, oh.
C1,
C1?
x to the negative third plus C2 x squared.
I like it. So it depends on what they ask you. They can ask you, the book likes to ask you what's the second function. You don't have to worry about any constants then. Right? This constant, I want you to realize there were some assumptions we made that leads to this constant happening, but it's just one possible constant. It really is C1, it could be anything.
If you're like dividing like C1 divided by 4 or like multiplying.
Yeah, you suck it in and make it C2 or
Yeah,
C3 if you already got a
C2
C2.
or
Yeah.
C3.
Yeah. I want to lay that groundwork now. I keep trying to make at least a note if you do something wrong with your constants, because later you're going to have to follow that chain of C5 was C4 plus 2, and C4 was 1/3 C3. Oh shit, you got to remember all that shit later.
Do you have to
Or very
evolve your constants, or can you just make it C1 divided by 4?
Well, you want your answer to be clean.
Okay.
I like that. Does that jive with, I mean, how would we do this now? Once we're out of 4-2, once we're into 4-7, right? Because what form is this in? Cauchy, Euler? So what would be the auxiliary equation?
Plus B minus A.
B minus A, I like it, so plus M minus 6 equals 0, and how do you factor that? M plus 3, M minus 2. So there's your M plus 3, gives you this. M minus 2 gives you that, right? So it'd be really, really nice if I gave you a problem like that you could actually check the newer way, right? Let's see if I feel like doing that. Because this idea of reduction of order actually goes further than some of the processes that we learn. Okay. That's reduction of order. Yes, sir.
I don't fully get how you got y2 from that. Like, how'd you make the distinction that y2 is just that piece of it?
Because the constant doesn't matter.
And the cx squared is what we already knew that was it.
We already knew that, and by putting a plus C, I kind of collected again. And I think the book, I don't remember now, but I think the book doesn't really put the plus C. It just captures the Y2. But I kind of always liked getting both of them in one go. But this is too specific. Let me see, what can I say there? There are some assumptions, where can I say? I mean, we left off a plus C there, right? I mean, I left off a plus C here that would have been absorbed into the coefficient here. It would have, I mean, it's already some assumptions going on. So that specific number doesn't even matter, to be honest. If you put a plus C here and I do E to both sides, doesn't that become a constant coefficient? And then this would just get absorbed into it. I like it. Yes?
So that's different. That's like different than yp when you figure out a particular solution for like if
Yes,
it wasn't
very
a-
different.
Yeah.
Yes, because with YP there won't be any C's in there. I like it. Okay. So that's reduction of order. So normally that one's really nice. Then we got into the first series of cases, which is just the constant coefficient stuff. That should be like, oh, yum, 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 right? Even if I gave it some gross, quadratic, complex, everybody should know. So what's the cases again here?
Real group, complexes.
Yeah, so if I got m equals 1, m equals negative 2, let me do this, and m equals 0. What would that relate to?
C1.
What would YC be?
C1
C1
plus
plus C3.
plus
C3.
I like it. And this is going to come about. Now, a big mistake that a lot of people are making is what's the thing with this and what's the thing with this? What's the auxiliary equation for both of those? What's the auxiliary equation for this? Because remember, you can't forget this. It's not that I'm making derivatives become powers. And if you forget why this works, part of your brain is going to go, oh yeah, derivatives are powers. No, see, that's crap. Right? This came from assuming the form of it being e to the mx. When you take derivatives, the m comes down. When you don't take a derivative, the m don't come down. Right? You guys with me? So I'm getting way too many people telling me this is m squared plus m, when really this is m squared plus 1 equals 0, yeah. So why does it make sense? When am I going to have a constant answer? When can there be a constant answer when there is no y? Right? If this was y equals y equals 0, could y be 5? Well, no. Could y be any constant? No. No, it can't. Shit. You guys see that? But if it's missing, can y be any constant? Oh, hell yeah. If y is 17 billion, what's y prime?
negative
0. And what's the second derivative? 0. 0 plus 0 is 0. That's why it makes sense that there's an m that I can pull off. Don't worry, you get over it. There's an m I can pull off. Do you guys see how it makes sense then? That's the only time you're going to have m equals 0 is when you're missing that non-derived part, the y by itself. Please let that make sense. So don't make that mistake anymore. Okay. What I'm thinking about doing is when I do a variation of parameters, I'm going to say verify that y1 and y2 are this. Because if you screw up y1 and y2, you have no chance, obviously. Right? If your y1 and y2 are wrong, you're screwed. Does that make some sense? Okay, maybe. Okay. So that's case 1. Case 2, what have I got? M1 equals M2 equals M3 equals negative 4. What will y see?
C1 e to the negative 4x plus C2 x e to the negative 4x plus C3 x squared e to the negative 4x.
Kick ass. I like it. So however many repeats you get, you just keep multiplying by another x. Yes?
Do we have to show our work for this, or can we use this shortcut?
So this is actually not a shortcut, to be honest. I mean, this is the method. And it's I can't make the distinction between, I don't consider this a shortcut because the work you would do to get here always is the same. The variation of parameters thing, not so. And the shortcut takes you all the way, it just skips a lot of shit, whereas this just skips some stuff that you should be able to do. I have no trouble using this shortcut because it's skipping stuff you got to be able to do. And again, remind me, where do those answers really come from? I mean, this one comes from there, and these two, of course, come from
U and Y.
E to the natural log next to the 4
reduction. So you'd have to kind of mess with it a bit, because I don't think you did a lot of third order, reduction of order kind of problems, but you could still get it. But that's where those two would come from. Okay, I like it. Maybe.
So the answer to number 2 on the practice test is just reduction of order?
Yeah, exactly. Yes, I love it. And then case 3, let's say you get m equals 3 plus or minus I squared root of 7 over 5. I like it. So we get this. And what would YC be? E to the 3/5 x cosine or sine, Pierce?
7 over 5 x.
Yeah, C1 good.
X.
X.
Plus C2.
C2. I like it. Now, of course, that's the one that I sort of said, I mean, I really didn't have the time to go over with you. Reprove Euler's identity. Euler's identity is so beautiful, obviously. It's built off of Taylor polynomials. If you took 280, your teacher would never went over it. That's horrible. This is one reason why I love teaching 280. I'm like, we finally can do this. We can do this. Yay. So it's just a reorganization of a bunch of shit you get from that e to the I stuff. Remember, in Euler's identity relates e to the I theta to cosine and sine. That's what it does, fundamentally. I like it. Just through equating Taylor polynomials, believe it or not. Okay. Now, what about, let's immediately do this. I think 4 is just guessing the answer and plugging it in, right? I want to go right to, and then I skipped 4-6 when I was teaching this because I like 4-7 immediately, or as soon as I can after this. Because it's got the same idea, right? So this is 4-3. 4-4 is those certain kind of functions that are on the other side, so you can assume the answers form. Take derivatives, plug it in, see what the A's and B's and C's are. If you forget somebody, you're going to get something that doesn't make any sense because the math doesn't have what it needs, right? So 4-7 would be Cauchy-Euler. That's going to be x squared. So ax squared y prime plus b, x y prime plus c, y equals 0. And of course it could be not equal to 0, but let's just do this first. And then the associated, what would the associated, or the auxiliary equation be here?
Squared.
Yeah, so of course you end up with the same idea. You end up with the 3 cases that are possible. Every time you use quadratic formula, you got 3 cases possible. Case 1 is the nice one.
Do we need to show any work to go from the first equation to the second equation, or just play straight in?
You can just go right in. Yeah, because the methods are based on the substitution, and we can substitute once x to the alpha. And so we've done everything, or x to the m, sorry. And then we've done everything. So we're golden, right? We've handled it for every possible situation. So we don't have to do that over and over and over again. The work that changes is based on what these numbers really are, right? So let's say I do all this work, I get this, I factor it, and then I get these. What does that relate to?
C1 e to the, or C1 x squared. To the -1.
Yeah, or C2 over x, whatever. I like it. Case 2, so I had M1 equal M2, let's say equal M3 equal, oh yeah, because I don't know if they did any with triple. What's your gut tell you? Let's say these are all -5.
C1x to the -5
C1x to -5?
plus ln, or C2 ln of x to the -5.
I like it.
I don't know what that is.
What do you think?
Natural.
I don't think, did they do anything like that?
C3.
Am I pushing it further than what they did?
It's the natural of x squared.
Yeah, it kind of makes sense every time. Sort of like here, you just keep multiplying it by x's, Here, it would be plus, yeah, they're plus, C3, x to the negative fifth, ln of x. Now that's different than ln x squared. ln of x squared is very different. The 2 can't come down, for example. Right?
It's ln of x times ln.
Yes, ln of x times ln of x. I like it. And I don't know if they made a, I don't think they made a point of that anywhere.
I think that's in one of the homework problems.
Good. I like it.
You can write that like ln of 2x or something like that there? Is ln of x times ln of x, and there's some way to...
No, unfortunately. You can't do that addition multiplication thing in reverse. Yeah. The product of 2 logs doesn't equal the log of anything. Yeah. Okay. Now, there's a problem on the practice test that I didn't put on the key just because I forgot, to be honest. Or I think I was thinking about saving paper or something, I don't know. But number 4D. Let's try this one out. You guys do the homogeneous associated case first. Oh yeah, why didn't you do case 3? All right, we'll look at that in a second. What's the auxiliary equation look like? M squared minus 9, good, just get b minus a, that's 0. Equals 0, so m is plus or minus 3. So then you get for y 1 and y2, what do you get? Y1 is just going to be, okay, and y2 is, okay. Now the big mistake people make here, I was having a discussion with this with somebody earlier today, is that, what do I need to do? Can I just get into ax squared? Like, can I just say y equals ax plus b and then do derivatives? Yay. What's wrong with that? Yeah, I've got to get in standard form. I don't know what the function is that I'm working with. I don't even know if it's something I'm allowed to do that undetermined coefficients thing with, because what's supposed to be here? 1. I like it. So when you divide by x squared, y double prime plus y prime over x minus 9y over x squared equals 4 over x. So now you can do, now what's f?
4 over x.
Yeah, so this will be f. Because here's your p of x, here's your q of x. Remember, we can't identify f of x until you've gotten 1 out front. And I think they do at least, I should do a couple examples. Yeah, like example 5 is a non-homogeneous, I think it's the only one that they do before they get freaky. Yeah. Example 5, they have to divide by x squared first before they start doing everything, the Wronskians and stuff. All right, so what's the Wronskian going to be here? I could do that before I did any of this over here.
It's going to be your y's.
Yeah, it's going to be based off of these.
Root squared or -4.
I know, man, it sucks. To change gears between forward and backward, derivative and antiderivative. This pure derivative. So then I get
-3 x to the negative 1, -3x to the negative 1.
not equal to 0 because we knew from the beginning x could not be 0. It can't be infinite either. It's not equal to 0. Well, that can't be 0 anyway, no matter what. So that's good. So that means that these are independent, and that's not what we're doing this for. Now we're going to use that Wronskian to do some stuff.
You're gonna.
And you can remember the shortcut. You don't have to do Wronskian 1, Wronskian 2. You don't have to do that, because it always comes out the same.
Speaking of that, are you gonna give us a third order? Because we kind of have to do that with the third order.
Yeah, I don't think I'll give you a third order. Yeah, it just sort of becomes a little bit of busy work with the determinants, unless I'm careful with it. I mean, I'm not going to do that to you. The process grows with the problem, right? And determinants get worse and worse the larger the matrix gets, of course, but the process doesn't give a shit. We care, because we have to write it all down. But the process doesn't change, which is nice. Yes?
Are we allowed any like formula sheet or anything like that?
No. Yes. Oh, I'm so evil. Yes?
Are we gonna have enough time to take this test? It seems like all the stuff in this section is a lot of like.
Yeah, it's a good thing I only did this one chapter.
Yeah.
It's really nice that we didn't get to 4.9 too. All right. So you have even more time than originally. Or I'll just think a couple problems in there and stuff. So what's U1 prime going to be?
W1 divided by the Wronskian.
Sure, W1 divided by the Wronskian. So I don't know how you memorize this. I'd rather for this, yeah, in general it's going to be
Negative y2 times f of x over w.
over W. So in this case it'll be negative x to the negative 3 times the function 4 over x divided by the Wronskian. And again, if you turned your Wronskian around, which means you assumed y1 was the other guy, y2 was the first guy, you guys with me, then everything kind of shifts with you. It still works out the same way. So what do I end up here with? The negatives go away. I get 2 over 3 x to the negative 4, x to, well, these kind of cancel out, right? So x to the negative 3.
Are you gonna put some 4-1 on the test or?
Well, 4-1 is sort of subsumed in all the other ones. But 4-1 is the get the ball rolling section. Well, once you've already rolled that ball down the hill and then back up and then down again and then back up. Who is that? Sisyphus? Anybody know the Greek mythology? No? The roll the ball and then just kind of, sure.
Working out.
I'd still say you got a better than Prometheus. Is everybody decent with it so far? This is what I would remember if I was you. Right, for U1 prime?
Isn't it the same thing?
Yeah, but it doesn't make you memorize this and work it out. You can just go straight to this. And again, don't lose sight of the fact that it works this way because of the assumptions we make. And why can we make those assumptions? Because there's an infinite number of possibilities. So I just chose the ones that were easiest to work with. In general, not always. Okay. I know some of you guys don't believe me, but oh well. And now I'm just going to iterate that. What do I get when I integrate that? 2/3 times what will become x to the x to the negative 2 over negative 2. So I get negative 1/3 x to the negative 2. What's U2 prime? It's going to be y1f over the Wronskian. So it'll be x cubed times 4 over x over, where'd it go? Negative 6 over x. So again, it'll be negative 2/3 x cubed. Stay with me now. So then U2,
flip that.
Well, what do you get when you integrate this though? Flip what piece? Oh, you flip this? Sure, of course. It's pretty cool this so far. I mean, again,
What's in the numerator?
here?
Yeah, I mean the denominator.
6.
Yeah, the Ron's. Yeah, the
Oh,
negative 6 over x, yeah.
that's good.
Okay, that's all right. I can still. The day I can't is the semester I retire. And then U2, some of you guys might be like, man, too bad it didn't happen right. U2 equals, when I integrate that I get x to the 4th, and then divide by 4, so it's going to cancel that. So it'll be negative 1/6 x to the 4th. So what really got this whole ball rolling, that you sort of don't write for yourself when you jump into the shortcut, but what really got the whole ball rolling was what? The assumption that y equals, what gets this whole thing going? Y equals, yeah, u1, y1 plus u2, y2. So now we've got u1, and we've got u2. So now we can just multiply those by y1 and y2 and be done with it. So what do we get? We get y equals, where'd it go? u1 third. Negative 1/3 x to negative 2 times x cubed plus negative 2/3 x cubed. Nope. Negative 1/6 x to the 4th times x to the negative 3rd. So I get negative x over 3 plus negative x over 6. It's neat. Yeah, I just get negative 1/2, negative x over 2. Yeah, okay. Yeah. And of course, you can always check your answer, right? Is that what you guys got or get? So I check this real quick. Remember, all this other shit's just going to make it 0. So I can forget about that for a second. When I look at y equal negative 1/2 x, so minus 9 x over 2. This would be plus x. Y prime would be,
Well, that's your YP, right?
yeah,
So that
Yep.
isn't your whole equation, that's just your YP.
that's just your YP. Exactly. So that's what should make this happen. Right? Plus x times y prime will just be negative 9 over 2. What's y double prime going to be? 0. So let's see, I get negative 9/2 x minus 9/2 x is negative 9x, which is not quite 4x. So
Isn't it 1/2?
maybe. Where are we looking?
Y prime is 1.
Y prime is 1/2 or negative.
Oh yeah. I'm looking at the stupid 9. All right. Let's see. Y prime would be negative 1/2.
When you multiply it, it becomes plus 9x over 2.
Oh yeah, the negative. Good. So now I get 4. I get 8x over 2, which is 4x. Thank God. Okay. Eventually it works. So of course, if you screw up on your check, like I just did, you'll be like, shit. So maybe slow down on the check. But just to remind you, I mean, sometimes you forget that when you get something, you can actually check it still at this level. Yeah.
Case 3,
Yeah.
4.7. If it's just a non-repeating complex root, it is just x to whatever cosine.
So in this
theta,
case, it would be what?
x to the 1, 1/2.
Yeah.
And then
Times C1 cosine of
2 over 2,
2 over 2.
x.
Uh,
Or, natural. Wait,
Log of x.
yeah, that was my question. So you add the natural log of x even though it's not repeating?
So now remember, what goes inside the cosine and sine for the constant coefficient case is an x. And that's the thing you actually multiply on the outside when you have a repeating thing. So you're thinking, quite the right way. This is related to that whole thing. Hopefully some of you guys did some of the homework where you do the x equals e to the c. There's a whole little example that shows you. That's the relationship between the exponential stuff and the x stuff that actually makes a Cauchy-Euler equation have constant coefficients if you replace x with e to the t. It's kind of a nifty thing, if you do it carefully, because dy, this is dy dx, right? So if you're replacing x with e to t, you better replace all your dx's with dt's. You have to be careful. It's actually a little chain rule thing you got to do. Whole little example that talks about it. Not a huge thing, but still, it kind of makes sense out of some of this stuff. The connection between your x stuff and your e to the x stuff, right? So then you get c2 sine 2 national.
Okay, I feel that.
And again, it's I know I didn't go all the way through it, but it's the whole idea of x to the m is equal to, who remembers this, e to the,
Natural log of x.
yeah, what's x equal to? X equals e to the ln x. So what's x to the m? It's going to be e to the ln of x to the m. But don't you just multiply powers when you raise powers to other powers? So x to the m is e to the m ln x, which you can call e to the t. Oh. And isn't this m ln x in a way? I mean, you know, the imaginary piece of the m. You guys kind of with me? So wouldn't that be related to cosine x like it is, you know, cosine t? Like it is, I mean, you guys. Okay, there's one O.
Oh, I see.
Yeah. There are connections that you do have to kind of make on your own. There's a reason there's a lot of sentences in there, in the book that was created. Yes?
For that last problem we just did, can you write out the general solution?
Yeah, what would the general solution be?
Y C1
Yeah, C1.
x cubed plus
So C's on these.
Minus x.
That's x over 2. Like. See if this shows. No. No, okay. All right, so let's see. What did I kind of skipped over 4-6. No, not really. We did 4-6. No, we basically just did that here as part of 4-7. So when you have a 4-6 is all about what if you want to do undetermined coefficients, but you have a function that you're not allowed to use, then that's variation of parameters. Undetermined coefficients is beautiful, but some of you guys, you got to remember a few things. So what are some things you got to remember about undetermined coefficients? They're pretty straightforward, except when. What's the first place where undetermined coefficients become less straightforward? There's a couple places, a couple answers I'll accept right now.
The products of functions?
Yeah, okay. So you have products of functions. So if you had a dE equals x cubed minus 3 times sine of 7x, what's your form going to be?
ax cubed plus bx squared plus cx plus d sine of 7x, and then same thing with cosine of 7x, but with, yeah.
Jeff has to remember. It's alphabet as you go on. Yeah. Shit.
Because you have to account for everything in between the x cubed and the function.
Yes, yes. And I was discussing before, if you have something like this, you gotta be careful when you try to do this, because it actually changes when there's shit out in front of this thing. But if you have just this basic thing, can you guys see what's going to happen here? If this was allowed to have a cosine in it,
That would be negative.
this would also have a cosine in it with a different coefficient, especially because that's 3, right? So it pretty much has to be some constant times sine. Now you got to be careful when you go down that road, because the minute I throw anything out front, you got those product rule pieces that can go together and kill each other, and if they're not there to begin with, if you think, oh, I only have to put a sign down, you're screwed. So what should you do in general? You say this is going to be a sine 3x plus b cosine 3x, and then go from there. I like it. There's that one problem. Number 5. Let's do number 5 right now, because I didn't have that on the answer key. Then I'll give the answer key stuff out, so you guys can look through that. 5 should be relatively quick. This is something we did before by observation, but now you can actually see it happen, which is nice. So what's the, so if I do this guy, what do I get here?
M equals plus or minus 4.
Yeah, m squared plus 16 equals 0. M equals plus or minus 4i. So we get yc equals, oh, let's just do this. Yes, yeah, yc equals
Cosine 4x plus sine.
yeah, c1 cosine 4x plus c2 sine 4x. Okay, I like it. There's no multiplier out front because it's 0, so you get the 0 is 1. Yeah.
What's that little a called again?
The alpha dude?
Alpha, yeah.
The real part? Yeah. Okay, I like it. Is everybody cool with that piece? Now what throws us off a little bit here?
You're going to have a yc is going to be in your yp.
Yeah, so I want to assume that this is y equal a sine 4x plus b cosine 4x. But,
ax.
yes, I have to use